Otherwise, I would like you to try these warm-up questions at the bottom of your homework. So question number 1, find this mistake in the solving of this inequality. It's a common mistake I see, so I'm trying to avoid it by showing you the mistake ahead of time. And then 2 and 3 are a preview of what we're working on today. For question 2, can you find a number that is greater than 4 and less than 10? In question 3, can you find a number that is less than 4 or bigger than 10? So pause the video now, maybe give everyone a minute to try these 3 questions, unpause it once we are ready to go. Okay, here we go. If you recall, the 3 steps for solving any equation and inequality is simplify, same side, solve. The first thing they did was simplify by distributing the 2 through, and they end up with 2x minus 8. That's correct. And they got their numbers to the same side by adding 8 to each side, or just noticing that the numbers are going to cancel out. And then they get 3x is less than 2x, and they've stopped too soon. They say, oh, 3 is less than 2. There's no solution, empty set. But the problem is they haven't even got their variables to the same side yet. You need to subtract 2x to get your variables to the same side. Then you'll end up with the statement x is less than 0. And that is the final answer. Any negative number would have made the original inequality true. So you can't stop short until you've got your variables on the same side. If you've got your variables on the same side and then your variables cancel out and you end up with a statement that 3 was less than 2, then you were correct if you wanted to say no solution, empty set. But here we hadn't even got our variables to the same side yet. So question number 2, is there a number that is bigger than 4 and less than 10? Yeah, there's a lot of them. You could do 5, you could do 6, you could do 9, you could do 4.1. Any number in between 4 and 10 would work. Is there a number that is less than 4 or bigger than 10? Yeah, there's also a lot of those. There's 3. 3 is less than 4 or bigger than 10. When we use the word or in math, you just need to be one or the other. What else would work? -7 would work. 11 would work. 10.1, 1,000. There are lots of numbers that are less than 4 or bigger than 10. You just need to be on one side or the other. If it said, is there any number that is less than 4 and greater than 10, then there is no solution. There is no number that is less than 4 and bigger than 10, but that's not what this said. This used the word or. With that being said, you then need your note packet out to section 5.4. Today we're working on what are called compound inequalities. Compound meaning more than one. If you take a chemistry class and you learn about compounds, compounds are formed when you combine multiple elements into one setting. Well, this is going to be combining multiple inequalities into one expression. That's why we call them compound inequalities, because there's more than one. Here's an example. At a Grizzly football game, this was about 5 or 6 years ago. The temperature at kickoff, picture shown, was a balmy 41 degrees in late November, early December. By halftime, it had dropped to 8 degrees, and you were in like a blizzard. Can you write a mathematical expression for the temperature at any point during the game between kickoff and halftime? Well, there's 2 things that we know. We know that the temperature, the lowest it got was 8 degrees, so it had to be bigger than or equal to 8, and the temperature had to be less than or equal to 41. It was somewhere in that range. So you could write it like this. This is one way you could write it. There's a fancy way that we can write 2 inequalities when they're in between 2 values. I'm going to show you that here. So another way that we could write this that's a little bit simplified is, instead of writing that t is less than or equal to 8, I hope you would agree that that's the exact same thing as if I said 8 is less than or equal to t. Saying that t is bigger than 8 is the same thing as saying 8 is less than t. I'm going to keep the right-hand side the same, and then you'll realize there's kind of some redundancy in the middle here. I've used t twice. I really don't need to write it twice. So instead of writing it twice, what I do is I just write it once. And then I put the ends as so. I have less than or equal to 8. So this is really read as 8 is smaller than t, and t is smaller than 41, which means that t is somewhere in between 8 and 41. So that's another way of writing that t is, the temperature was in between 8 and 41. So this is an example of a compound inequality. It is less than 41 and bigger than 8, because 8 is smaller than the temperature. We call this an and compound inequality, because you have to be bigger than 8 and less than 41. So the first thing that we're going to do is just practice graphing compound inequalities. An and compound inequality is also called an intersection, because it's where 2 of these items overlap. So I'm going to use some colors to show what's going on here. So I'm going to do this first one in green. I need to be bigger than 4, so I do an open circle around 4, and I know I need a shade heading to the right of 4. And I need to be less than 10. So open circle around 10, I need to be less than 10. And where would these overlap? They would overlap in the middle. So all of these numbers right in between are all of the numbers that are bigger than 4 and less than 10. So we call this an intersection because it would be where these items overlap. It's where they cross. The other type of compound inequality is called an or a union. First one, I need to be less than 4, so open circle heading to the left of 4, or bigger than 10, open circle around 10, heading to the right of 10. You'll see that these do not intersect, so we call this a union. It's just the combination, the combining of the two. You get both of them, like for a union being a marriage, you would bring the two together and you get both of the items. So we have less than 4 or bigger than 10. An or is called a union, and is called an intersection compound inequality. Compound inequalities, vocab word, I kind of already mentioned this already. They are two separate inequalities that are joined by either an and or an or statement. An and statement is also called an intersection because it's where two inequalities overlap. An or compound inequality you'll also hear called a union because it's where two of them are brought together to make one. An example of an and would be I need to be bigger than -2 and less than or equal to 1. So I take both of these separate inequalities written right here and I combine them to make 1. When I graph it, it would look something like this. They are connected in the middle. If I have an or statement, I might be bigger than or equal to 0 or less than -1. These don't overlap, so these kind of shoot out either side. They remind me of like the lightsabers in the newer Star Wars films. So that would be an or statement. You'll realize there is no shorthand way to write an or. The only way to write an or statement is to use the word or. The reason why is because they do not overlap. An and statement can be written as one because they actually cross. So there's no shorthand way of writing an or, whereas there is a shorthand way of writing an and. So be aware of that. First thing we're going to practice is just translating from English to math and then graphing. So first example says a number p is greater than -2 and less than 3. So I'm going to write this out the long way and then do the shorthand. So p is greater than -2 and p is less than 3. So that means p is somewhere between -2 and 3. I could write this the shorthand way by saying that, hey, that means that -2 is less than p and p is less than 3. And if I notice, these p's in the middle are kind of redundant, so I could write the final statement as saying that p is somewhere in between -2 and 3. I do an open circle around -2. I need to be to the right of -2. That's what the first statement said. Open circle around 3 to the left of 3 because I'm less than 3. These are going to combine in the middle, and the numbers that are bigger than -2 and less than 3 are in between. And this is what an and statement would look like. This is also known as an intersection because it's where they cross. Like an intersection of two roads is where the two roads cross. So it's an and. You can also say it's an intersection. I'm going to give you a chance to try. So pull out your whiteboard. Your job is to translate and then graph the following, exactly what I just did. Translate a number x is less than or equal to 10 or greater than 35. So translate it to a mathematical statement and then graph it on like a number line. So pause the video now for maybe a minute. Unpause it once everyone's had a chance to try. Okay, this is what you should have got. The graph looks like this. Here is what the statement would look like. The statement would be, it says number x is less than or equal to 10 or x is greater than 35. And there's no shorthand way of writing this. You can't try to write it like this. It would not work. It wouldn't be the same thing. If you tried to write it like that, it wouldn't be the same thing. You can't write an or statement in a shorthand way. You have to use the word or. So that is as simplified as you can write that statement. And then the graph for it would be shown below. An or statement, they shoot out either side because there is no intersection in the middle. I need to be less than or equal to 10, so filled in circle at 10, or bigger than 35. If I pick any number that is bigger than 35 or less than or equal to 10, I will have satisfied the statement. So 9 would work, -3 would work, 40 would work, 22 would not work because that is not less than or equal to 10 or bigger than 35. It's actually in the middle. Now that we know how to graph it, we're going to practice solving them. So the first one we're going to try to solve is solving a compound inequality with and. So let's say I have the statement that x plus 5 is essentially in between 2 and 9. And I want to know what values for x would make the original statement true. So what can I do with an and statement? Well, I can split it into the two statements that it actually is. So I'm going to show you two ways of solving an and. This first way is a little longer, but it'll make you appreciate the shorter way here in a moment. So I can split this into two and statements. 2 is less than x plus 5 and x plus 5 is less than 9. Now I just solve them individually. How do I solve them? Subtract 5 from each side. Over here on the left, I'm going to end up with negative 3 is less than x. Over here, if I subtract 5 from each side, subtract 5 as shown in red, I end up with x is less than 4. Now I have that negative 3 is less than x and x is less than 4, so I can put that back together and say my final answer is that x needs to be any number in between negative 3 and 4. I can't pick negative 3 and 4 because those are not equal to statements. How can I always check? I can always check by picking a value and substituting in. What's a nice, easy number to check in between negative 3 and 4? How about 0? If I put 0 in here, I end up with 0 plus 5 is 5. And is 5 somewhere between 2 and 9? Yes, it is. 5 is bigger than 2 and less than 9, so 0 works. Any number in between negative 3 and 4, not including those numbers, would work. So there is my solution set, any number in that shaded in region. So that's one way of solving an and, is to split it into the two statements. But you might have realized I did the exact same step here. I subtracted 5 from both sides when I split it. So why not just do it together? So what do I mean by that? Well, how do I get x alone? In the middle, I would need to subtract 5. So if I subtract it from the middle, I need to do it to the outsides. You've always heard in algebra what you do to one side, you have to do to the other. In a compound and inequality, the two sides are the inside and the outside statement. So if I do it to the middle, I have to do it to the outsides, both sides of the outside. So if I subtract 5 from the middle, then I have only my variable terms in the middle, which is what I want. I end up with x in the middle. 9 minus 5 is 4. 2 minus 5 is negative 3, and voila, I get the exact same answer that I got before without having to split it into the two statements and then just put it back together anyway. So the quicker way to solve an and statement is just to whatever you're doing to the middle, do to the outsides. It's the exact same algebra steps you use when solving an equation. And that's how you solve an and statement. Now, how do you solve an or statement? Well, the easy part about an or statement is it's just like solving two simpler inequalities from like section 5.3 or the prior section, whatever that would have been. So here you just really have two problems in one. If I have 2x plus 3 is less than 9 or 3x minus 6 is greater than 12, I just solve them individually, one at a time. So simplify, there's no distribution to be done. Now I need same side. I need to subtract my 3. I end up then with 2x is less than 6. Last step is divide by 2. And then I get x is less than 3. So there's half of it. I have x is less than 3, or over here I add 6 to each side. I end up with 3x is greater than 18, divide by 3. I end up with or x is bigger than 6. I need to pick a number that is less than 3 or bigger than 6 in order for it to satisfy one or the other of the statements. So less than 3 or bigger than 6. So this is the 6, this is the 3. If I pick a number less than 3, it will make the left one true. It won't make the right one true, but you only need to make one or the other true in an or statement. If I pick a number bigger than 6, like 7, let's try. If I put 7 into both of the statements, right, I have 2x plus 3 is less than 9, or 3x minus 6 is greater than 12, I want to check the number 7. See that it'll make one of them true. If I put it into the right one and the left one, and then check them both, I end up with what? 14 plus 3 is 17. I get 17 is less than 9, or over here 3 times 7 is 21. 21 minus 6 is 15. I get 15 is greater than 12. So I have 17 is less than 9. That's certainly not true. Or 15 is greater than 12. That one's true. As long as one of them is true in an or statement, I'm good. In mathematics, an or statement is just one of them needs to be true. If it was an and statement, both of them would have to be true because and means both. or means one or the other. So if I pick a number bigger than 6, it will make the right one true. If I pick a number less than 3, it'll make the left one true, but I just need to make one or the other of them true. Last part, I'm going to ask you to try. On your whiteboard, pull it out. I'd like you to try an or and an and then graph them both. And then the last part we have to talk about is one special case. So pause the video now for maybe 2 minutes. You need to solve each, one or statement, one and statement, and then graph your solution. So pause the video now for 2 minutes, unpause it once everyone's had a chance to try, check their answer with a neighbor. Okay, I'm going to go kind of fast. This or statement, subtract 1, I get 3h is less than negative 6. Divide by 3, I get h is less than negative 2. Over here, add 5, I get 2h is greater than 12. Divide by 2, h is greater than 6. This is an or statement all along, so on my number line, I have to be less than negative 2 or greater than 6. Over here, this is an and statement. So the first thing I need to do is get all of my numbers to the outside. So get rid of the plus 4 by subtracting 4 from all sides. I then get 6 is less than or equal to 2y is less than or equal to 20. Last step, divide all sides by 2, inside and outside. So I get that y has to be a number somewhere between 3 and 10. Circles, I need to be bigger than 3 and less than 10. And then I can be equal to 3 and 10, so I fill those in. And there would be my solution sets. Last one in the note packet is a special case. What if I ask you to graph the answers for x minus 23 is bigger than negative 10 and x minus 16 is less than negative 20? So I'm going to solve both of these. Add 23. I then end up getting x is bigger than 13 and add 16. I get less than negative 4. And then I ask myself, if I try to graph this on a number line, I want all the numbers that are less than negative 4 and bigger than 13. Well, this is actually going to start to make an or statement. Like if I try to graph this, it's going to look something like that. But I need it to be an and statement. There are no numbers that are less than negative 4 and bigger than 13. You'll see, because if you graph it, it starts to make an or. So that means if there are no numbers that do this, we'd say this is a no solution. There are no numbers that are less than negative 4 and bigger than 13. So there's your unique cases.